In this video, I want to have a look at experimental probability. So experimental probability is also sometimes called relative probability because it's based on relative frequencies. And experimental probability is calculated based on the results of a trial or an experiment that we've run multiple times. So rather than being based on theory, on theoretically what should happen, experimental probability is based on what's actually happened in real life. So we use a very similar but slightly different formula for this one. So the probability of an event occurring is going to be the frequency or the relative frequency, the number of times that event actually occurred in our trial, divided by the total number of trials. All right, so we have a look at some examples. Our first one says that Chris recorded the first 60 vehicles to pass through an intersection, and he's drawn that up in the table just here. It says based on these results, determine the experimental probability that the next vehicle to pass through the intersection will be a truck. So we know that all up these add up to 60, so there's a total of 60 vehicles that passed through this intersection. Of those, 6 of them were trucks. So that means the probability, the experimental probability that the next one will be a truck, so we'll write the probability of T for truck, will be 6, because there were 6 trucks out of a total of 60, so 6 over 60. And we could simplify that down to 1 over 10. Right, the next one would be the probability of a motorbike, so the probability of M. There were 9 motorbikes, so we can write that as 9 over 60. And again, we could simplify that down. If we divide top and bottom both by 3, we'd have 3 over 20. The next one asks us the probability of a bus or a truck, so we can write probability of B or T. So a bus was 3 and a truck was 6. So together, the relative frequency of either a truck or a bus was 9 out of a total of that same 60. So again, that would simplify down to 3 over 20. And the next one is not a car. So we could write probability, well, not a car means it either has to be a truck, a bus, or a motorbike. So we could write the probability of T, B, or M. Or we could use that notation we learnt where we do the little squiggle over the top, which means not a car. So the probability of not a car has to be either truck, bus, or motorbike. It's got to be everything else. So if we add those together, 6 plus 3 is 9, and 9 plus 9 is 18. So we would have 18 over 60, and that will simplify down to, 6 over 20, which can simplify again to 3 over 10. All right, we have one more example. So in this one, we've got Jess rolled a die 100 times and recorded her results. So this is the number that she got on the die, and this is the number of times she got each of those. So there were 17 times where she rolled a 1, for example. It says, based on these results, calculate the experimental probability of rolling a 3. So the experimental probability of rolling a 3 would be, well, we got 14 3s, so we'd have 14 in the numerator, out of a total, and we know that those numbers add up to 100 because she rolled it 100 times. So 14 over 100. Then it asks for an even number, so the probability of even. Well, that's got to be our 2, our 4, or our 6. So we've got our 20, 18, and 12, 50. So that's 50 out of 100. And the next one, we've got a probability of a number greater than 4. So if it says greater than 4, we don't want 4 included in that. We would just want things that are greater than 4. So that's our 5 and our 6. So that would be 19 plus 12 would be 31 out of 100. All right, the next question, part B, asks us to calculate the theoretical probability of rolling these things. So this time we're not using this table, we're thinking theoretically how many times should you roll these things. So the theoretical probability of rolling a 3, well, there's 6 possible outcomes we could have, and only one of them is a 3, so that would be a 1 out of 6. The probability of rolling an even number, well, there's 3 even numbers out of a total of 6, so we should have 3 over 6, which is equal to a half. And a number greater than 4, well, there's only 5 or 6, so there's 2 possible outcomes there. So we would have 2 out of 6 there, or 1 over 3. Now, part C asks us, are the experimental probabilities and theoretical probabilities that we got for those 2 sections similar? Now, at the moment, it's a little bit hard to compare, say, the fraction 14 over 100 to 1 over 6. So what we're going to do is convert those to decimals. So 14 out of 100 actually converts to 0.14. 50 over 100 converts to 0.5. And 31 over 100 converts to 0.31. Converting our theoretical probabilities as well. 1 over 6 converts to about, not exactly, but if we round it to 2 decimal places, about 0.17. A half is 0.5. And a third is, again, approximately 0.3. So these ones are rounded off because those decimals will go on forever. But that makes it a little bit easier to compare the two. So you can see that the probability of an even number actually worked out to be exactly the same. The probability of a number greater than 4 worked out to be pretty close, 0.3 and 0.31. That's pretty close. This, if we'd written it to 2 decimal places, would have actually been 0.33. And our top one, 0.17 and 0.14. So that's pretty close as well. So it's not exactly accurate, but they are fairly similar. Right, so that's a look at experimental probabilities.